The pressure dependence of delta G can be demonstrated with a simple chemical system that involves NO2 gas and N2O4 gas. This syringe shows the NO2, N2O4 equilibrium system where NO2 is the brown color and N2O4 is colorless. This system, it has a volume of 10 milliliters and a pressure of 1 atmosphere. Then when the syringe is depressed, the volume is cut in half to 5 milliliters and the pressure doubles to 2 atmospheres. And the color becomes darker brown because the NO2 is at higher concentration, being that the total volume is only 5 milliliters now, than it was when the total volume was at 10 milliliters. But then after a few seconds, something really interesting happens. The color of the gas lightens. And this is because the equilibrium has been shifted to the right, favoring more N2O4, which is colorless, and less NO2, causing less brown color. Now, in Chem 1A, this process was explained in terms of Le Chatelier's principle, which says that when an outside stress is put upon an equilibrium, the equilibrium system reacts in such a way as to minimize that stress. But now we're going to explain this observation in terms of delta G. And since delta G tells us the spontaneity of a reaction, we can see that by increasing the pressure we have shifted the reaction to the right, thus favoring more N2O4, which suggests that the reaction has become more spontaneous under higher pressures. In the following video, this same process is demonstrated with some interesting graphics.
A syringe is filled with a mixture of nitrogen dioxide, NO2, and dinitrogen tetroxide, N2O4 gases. It is plugged so that no gas can escape. The system is in equilibrium. NO2 is a brown gas, and N2O4 is colorless. So the more NO2 is present, the darker brown the color of the syringe. When the gas is rapidly compressed, the color first turns darker brown and then gets slightly lighter. It ends up darker than it was before compression. When the gas is rapidly decompressed, it becomes lighter, then gets slightly darker. It ends up lighter than it was before decompression. How do we explain these results? The initial change in color results because when the gas is compressed, it is more concentrated, so that its color is darker. The gas will react to the pressure change as predicted by Le Chatelier's principle by reducing the number of gas molecules. 2 NO2 molecules will combine to make 1 N2O4. This takes a bit of time to happen, so the color fades gradually as the brown NO2 reacts and the pressure decreases slightly. When the gas is decompressed, it is less concentrated so that its color is lighter. As predicted by Le Chatelier's principle, the system will respond by trying to increase the pressure. To do this, it must make more gas molecules, so some colorless N2O4 will break up into brown NO2. This takes time to happen, so the color increases gradually and the pressure increases slightly.
To calculate the delta G of the reaction when the pressure changes, we have to understand non-standard conditions, because standard conditions are defined as 1 atmosphere. But once the pressure changes, then the conditions are no longer standard, and it results in a different delta G and a different spontaneity. So we have to back up and look at the tendency of chemical reactions, which is that they do not continue to completion. 100% of reactants do not necessarily turn into 100% products. They seem to stop at a certain point with no observed change in quantities of reactants and products. The reaction has reached chemical equilibrium. So we need to determine the free energy of non-pure systems to understand why chemical reactions reach equilibrium, or why they're shifted in one direction or another in order to reach equilibrium. First of all, let's define equilibrium and demonstrate it. Here's a reaction where A is turning to B, and let's say this reaction is spontaneous, meaning that delta G under standard conditions is negative. And the reaction starts with 100% A at 1 atmosphere, and it's going to end up at 100% B at 1 atmosphere. And so we allow the reaction to occur, and you can see that some of the A molecules are turning into B molecules. But as soon as enough B molecules are formed, they start reacting backward to form A molecules, so that the reaction rate forward going from A to B is the same as the reaction rate backward going from B to A. And this can be shown with a time plot where the partial pressure of A starts at 1 atmosphere and decreases until it reaches some constant level, and the partial pressure of B starts at 0 atmospheres and increases until it reaches some constant level. And then going forward, the ratio of these two remains constant, and this is called the equilibrium constant, defined as the partial pressure of the products over the partial pressure of the reactants, in this case K equals 2. The reason that chemical systems reach equilibrium, which represents some mixture of reactants and products, is due to the fact that the entropy of mixtures is higher, and higher entropy favors spontaneous processes. Let's consider 1 mole of an ideal gas at constant temperature, and we can subject this gas to some physical change, whether it's changing volume or changing pressure, and the entropy change associated with that process is going to be equal to the final entropy, or the entropy of state 2, minus the initial entropy, or the entropy of state 1. And this is given by the gas constant times the natural log of V2 over V1, or the gas constant times the natural log of P1 over P2. Now notice the inverse relationship between volume and pressure, and that's due to the ideal gas law. And so substituting P1 equals 1 atmosphere, which is our reference state, and S1, which would be the standard molar entropy. P2 would be any pressure that we choose, and S2 is the non-standard entropy. We find that the non-standard entropy is equal to the standard entropy minus the gas constant times the natural log of the new pressure divided by the reference state, and this is for 1 mole of an ideal gas. Notice that as the pressure goes down and becomes less than 1, the natural log becomes negative, and this term turns positive, thereby increasing non-standard S relative to standard S. When the pressure goes down, the partial pressure, that means that there's more other components contributing to the pressure, and so the partial pressure of any one component is decreased, thereby increasing the entropy of that system. The general result is that the non-standard entropy is equal to the standard entropy minus R times the natural log of activity, where activity for gases is the pressure of that gas divided by the reference state of 1 atmosphere. For solutes in solution, the activity is the concentration of the solute divided by the reference state of 1 molar, and for pure solids or liquids, they have an activity of 1 because they are not mixtures. The bottom line to remember is that mixtures have higher entropies than pure substances, and that gives rise to a more negative delta G when mixtures are involved relative to pure substances. Now we need to incorporate the expression for non-standard entropy into an expression for non-standard free energy for a chemical reaction. So if we have a chemically reactive mixture of reactants and products, for each compound that is present at any given time, the free energy of that compound must include the concentration and pressure effects through entropy. As the pressure and concentration changes over the course of a reaction, the free energy, G, is also going to change. And so we start with our general equation for free energy, which is G equals H minus TS. And now we have non-standard G, and that's equal to standard H minus T times non-standard S. It turns out H is not dependent on pressure, so we can leave it in its standard form. Now we substitute in the expression for non-standard S right here, which from the previous slide is standard S minus the gas constant times the natural log of the activity. And rearranging gives us standard H minus T times standard S plus RT times the natural log of the activity, which can be further reduced because standard H minus T times standard S is simply standard G. So non-standard G equals standard G plus the gas constant times the temperature in Kelvin times the natural log of the activity, where the activity for gases is just going to be its partial pressure, and the activity for solutes in solution is going to be its concentration. And so for every component in the system, we have a G, and this gives rise to this very important equation, which says that the change in free energy for any chemical reaction at non-standard conditions, or taking into account the pressure effects, is equal to the enthalpy change under standard conditions, 1 atmosphere pressure, 298 K, plus this correction factor, which is the gas constant, the temperature, and this Q value. And Q is a ratio of the activities of the products divided by the activities of the reactants, and each of these are raised to their stoichiometric coefficients. We'll be working with Q a little bit more shortly, but a nice result is that we can relate the free energy under standard conditions to the equilibrium constant by saying that from the second law, at equilibrium, delta G equals 0. There's no free energy change for a reaction that is at equilibrium, no driving force. And so Q equals the equilibrium constant, because the equilibrium constant is expressed in a very similar way to Q. And so this equation here reduces down to the free energy under standard conditions equals minus the gas constant times the temperature in Kelvin times the natural log of the equilibrium constant. So an analogy to a chemical reaction that includes these pressure effects is balls rolling down two types of hills. In the first case, we have a ball going from starting point of A to ending point of B, and this is if we only had the delta G under standard conditions term. We're going from 1 atmosphere of A to 1 atmosphere of B. In this case, it is spontaneous. However, if we include the correction factor of RT, ln, Q, we see a shape of a curve that looks something like this, where all the reactants A going to products B is still spontaneous, negative delta G. However, equilibrium lies at an even lower free energy position, C, where there is some B present because of the increased entropy due to a mixture. Now this next slide shows the relationship between Q and K and explains this very important equation in detail. Delta G under non-standard conditions, remember that it's going to vary as the reaction progresses. Delta G is constant at a fixed temperature, and it is defined as reactants and products in their standard states, 1 atmosphere for each of those. The Q is called the reaction quotient, and it influences the direction a reaction will proceed given some initial partial pressures. And so what do we mean by that? Well, this graph shows a plot of delta G as a reaction progresses from 100% reactants to 100% products. The value of Q when we have 100% reactants is 0, because Q is defined as the amounts of the products over the amounts of the reactants. So if the products are 0 and the reactants are whatever they are, starting conditions, the value of Q is going to be 0. Whereas when we have all products, we would have a number over the amount of reactants, which is 0, so 1 over 0 is infinity. Somewhere in the middle is where Q equals 1, where both the reactants and products are starting out at 1 atmosphere. In this case, the reaction is non-spontaneous. Delta G standard conditions is positive. And you can see that the reaction is going to go backwards to get to equilibrium. There's simply too many products when they're all at 1 atmosphere. And some of those products have to be turned into reactants to send the reaction backwards because delta G is positive under standard conditions. However, if we start with very few products and many reactants, then the reaction is actually spontaneous going toward equilibrium. If we look at a different reaction which is spontaneous under standard conditions, where delta G0 is less than 0, we can see where Q equals 1, the reaction still needs to go forward to reach equilibrium. If the products have built up too much, then the reaction will go backwards to reach equilibrium. Now let's work a problem that will demonstrate some of these concepts and make it more obvious to you. So now we're going to calculate the delta G of the reaction of 2NO2 gas in equilibrium with N2O4. And under standard conditions, this reaction has a delta G of minus 4.75 kilojoules. The equation we're going to use to calculate the non-standard state delta G is delta G under non-standard conditions equals delta G under standard conditions plus R times temperature times the natural log of Q. Now for this particular reaction, Q equals the partial pressure of the products, which is N2O4, divided by the partial pressure of NO2. Now notice that because there's a coefficient of 2 in front of NO2, this term has to be squared. So now using this formula, let's calculate delta G, and let's assume that the pressure of N2O4 and the pressure of NO2 are both 1 atmosphere. So let's assume P gas equals 1 atmosphere, and so the equation turns into delta G equals delta G0, which is minus 4750 joules plus 8.314 joule per K times the natural log of 1 divided by 1 squared. And you can see that natural log of 1 is 0, so this whole term is, oh, I forgot the temperature in there, so let's add that in at 298. We'll assume 298K. And so this whole term is 0. And so then delta G equals minus 4750 joules, which equals delta G 0. So the definition of delta G 0 is when the partial pressures are both at 1 atmosphere. So according to this result, delta G equals minus 4750 joules, this reaction as written is spontaneous right here. And so when you mix 1 atmosphere of N2O4 with 1 atmosphere of NO2, the reaction quickly shifts to the right to give you more N2O4 and less NO2. We can calculate the extent of that shift by calculating the equilibrium constant. And we can do that right now relatively easily. We're given this equation, delta G0 equals minus RT ln equilibrium constant, and rearranging we get K equals E to the minus delta G0 over RT. And for our particular reaction, that gives us E to the minus 4750 joules over 8.314 over 298, leaving off the units for simplicity. And that comes out to 6.8. So that is an equilibrium constant greater than 1, which means that it is product favored. Not very strongly product favored, since that number is not that much greater than 1. And we know that the expression for the equilibrium constant is the same as that for Q. The equilibrium constant is just a special case of Q at equilibrium. And that's going to be equal to the partial pressure of N2O4 divided by the partial pressure squared of NO2. And that equals what we just found, 6.8. Now we can go ahead and calculate the equilibrium partial pressures of N2O4 and NO2 by setting up an ice table. So the first thing we do is write our equilibrium. 2NO2 is in equilibrium with N2O4, and we write ICE, and we're assuming initial partial pressures of 1 atmosphere. And the change, we know N2O4 goes up because the reaction was spontaneous in the forward direction, so that's plus X. And we know that NO2 is going to go down by the amount double because of the coefficient there, so that's minus 2X. So at equilibrium, the amount is going to be 1 minus 2X, and here it's going to be 1 plus X. So K then equals 1 plus X over 1 minus 2X squared. Okay, unfortunately we have to use the quadratic formula, but nowadays that's not too tricky. So 1 plus X over 1 minus 4X plus 4X squared. And so that when we set that equal to the value that we found, we get 6.8 equals 1 plus X over 1 minus 4X plus 4X squared. And we get an expression of 5.8 minus 28.2x plus 27.2x squared equals 0. We get two possible solutions. X1 equals 0.754. X2 equals 0.283. Now only one of these can be physically possible. We look at the concentration at equilibrium for NO2 and we see it's 1 minus 2x. Well, 2 times 0.754 is about 1.5. So this one can't be physically possible because we can't have negative pressure. This one is possible, and so that is going to be the solution. And so then we can calculate the equilibrium partial pressures of each component. P NO2 equals 1 minus 2 times 0.283, and that equals 0.434 atmospheres, and P N2O4 equals 1 plus 0.283, which equals 1.283 atmospheres. So when they are mixed at 1 atmosphere each, the reaction changes to reach an equilibrium where there's still some NO2 present. This is at 298 K, but it is mostly N2O4. Now we're going to calculate the delta G when the syringe becomes pressurized. So when the NO2 N2O4 equilibrium undergoes a high pressure change, how does it respond? Well, we know from Le Chatelier's principle that it's going to favor the low pressure side of the equilibrium. So as the pressure is increased, the equilibrium is going to shift to the right to favor the product that only has 1 mole of gas as opposed to the reactant which has 2 moles of gas. But let's go ahead and show that using delta G. So delta G, let's assume 10 atmospheres of each, P of the gas, and we'll calculate a new delta G. That's going to be equal to delta G0, which from before is 4750 joules plus 8.314 times 298 times the natural log of the partial pressure of the product, which is 10, and over the partial pressure of the reactant, which is 10 squared. And so now this whole term right here, because it's natural log of a number less than 1, is negative minus 5705 joules. And so now we compare with the minus 4750, and we can see that the delta G, when we're at 10 atmospheres, equals minus 10.45 kilojoules. Indeed, the reaction has a more negative delta G than the standard delta G, so the reaction shifts toward the products as is indicated by Le Chatelier's principle. But let's look at the opposite process where we lower the pressure, and we'll see that we get a completely different result. So here's our equilibrium, and now we're going to lower the overall pressure, and we'll see that the equilibrium is going to shift this way to the left because it's going to favor the reactant, which is of a higher pressure since there's 2 of them, whereas the product is at a lower pressure since there's only 1. So we're going to decrease the pressure, and now we're going to calculate a new delta G, and let's once again write down our assumptions. Assume 0.1 atmosphere is the pressure of the gas. So now delta G equals minus 4750, the delta G0, plus 8.314 times the temperature, 298, times the natural log of the product, which is 0.1 over the reactant, which is 0.1 squared. See, now the natural log of a number greater than 1 is positive, making this whole term positive at plus 5705. This is enough to offset delta G0, and so delta G at 0.1 atmosphere equals plus 955 joules, sorry, just joules, and this means that the reaction shifts to the left as was predicted by Le Chatelier's principle.